We must change the time of this class in the following, but let me review some note and definition that we expressed in the previous section. In the definition of topology, a subset of P of X such that have these three property, every member of a topology is called open set. Okay, so that we have this let tau be a topology. Let tau be a topology on X. We have A is a member of tau if and only if A is an open set with respect to tau. Okay, A is open if and only if A belongs to tau, and this pair is called a topological space. Okay, topological space. And in this definition or example, Euclidean topology, we see that as an example. Okay, let x equal to real numbers and tau equal to these sets or these subsets of real numbers. The set of all subsets of real numbers such that there exists a family of balls or in open intervals such as this. such that A equal to this union. Okay. We said that tau is a topology on R. Okay. The set of all subset of R such that A can be represented as this form by this union. Okay. This tau is a topology because at first we see that empty set equal to this union such as this. Okay. And so that this is belong to tau and whole of R equal to this union, and this is belong to tau two. Okay, because this set have this form. Okay, for the second property of topology, let, for example, this is a family in tau. Okay, we must prove that the union of these sets belong to tau. Then for each index I, A and index I is a member of tau. Okay, all of this must be belong to tau, so that a I must be written as this union, so that for each I there exists a family such as A alpha, B I alpha, alpha belong to for example, we can write this set, because this set must be depend on I. Okay, such that this AI equal to this union B A alpha belong to I, okay. And finally, the union of these sets, okay, equal to this union, but this AI equal to this union itself, okay. Alpha belong to AI, and we see that this union is a member of tau because written as a union of intervals. This is a union of intervals, okay, again, so that for each family of members of tau, its union is a member of tau again. And this is the second property for topology. And 3, let's for example A1 and A2 belong to 2. Then there exists two sequences such as B1 alpha belong to I, and A2 alpha and B2 alpha belong to J, such that A1 equal to this union 1 alpha belong to I, and A2 equal to this union alpha belong to J, so that this intersection equal to the intersection of these sets, this and this. alpha belong to I, alpha belong to J. Let me write this intersection by this, for example. And so this intersection equal to this, because A1 equal to this and A2 equal to this, and this is equal to this union. A belong to I, we can write this as beta, this beta, beta, okay? And all of this change to beta or any index, okay? Okay, okay. Beta belong to J, and this intersection A1 alpha B1 alpha intersection by A2 beta and B2 beta. This equal to this, and this is an interval, okay? This is an interval for empty set, because these two are open sets, okay? Its intersection may be empty set or again a interval, an interval, okay? Okay? So that this intersection write as a union of intervals again, so that this is an element of tau. And so for each element of tau, such as A1 and A2, A1 intersect by A2 belong to tau. You can write this index as this form or this form or other forms, okay? But these intervals depend to 1, okay? Because its union must be equal to A1, and this index must be depend to 2. Okay. So that if we consider x equal to r and tau defined by this set, this tau is a topology. This topology is called Euclidean topology, okay? And similarly, you can consider this example. X equal to r to the power of n and tau equal to the set of all subsets of Rn such that A is a union of balls, okay? Balls in Rn. Balls or open intervals, okay? Intervals. Open intervals. Open intervals. These two sets are equal, balls or open intervals, but an open intervals in Rn have this form: open interval. Okay, is an open interval in Rn. Okay, so that in the case n equals 1, we have this open interval. In the case n equals 2, we have this a1, b1, a2, b2, and so that we have this as open intervals. And in the case n equal to 3, we have this, for example, okay, a cube, but not its boundary, okay, open cube. This is a1, b1 multiplied by a2, b2, and this is a1, b1 multiplied by a2, b2 multiplied by a3, b3, and other dimension. Okay, and this tau is a topology on Rn. Its proof is similar to the previous example. Okay, and this is the definition of Euclidean topology on Rn. Okay. For example, for example, these sets is in the Euclidean or natural topology. Okay. On real numbers, because this is proof. You can write this by this union. Okay. So that this set is a union of intervals, open intervals. Or similarly, this set is in the Euclidean topology or is open, okay, in this topology, open, because please note that for any topology on X, A belongs to tau if and only if A is open with respect to tau, okay? So that we can say that this set is in this topology or this is an open set in this topology. This is open because we see that this is equal to, for example, this union. Okay. Radical 2 minus n, and this is very trivial that if we consider this, then this union equal to this open set. Okay, and also, for example, you can say that this set is open because this is this set, if we consider this as A, this A is a union of intervals, okay? N plus 1, n from 1 up to the infinity. This is a open set. This is an element of 2. Okay? Welcome, Miss Habe. Miss Habe, do you have my voice? Mrs. Habe, do you have my voice? Okay. Okay, thank you. So that this set is open, or for example, this set R minus Z, real numbers minus integers, is open in Euclidean topology, because this is very nice, because this set equal to this union. Okay? Please note that this for example, if we omit integers, we have these open intervals. For example, 0, 1, 2, 3, -1, -2, -3. If we omit this integer, we have these open intervals. Okay? Okay? So that R minus Z equal to this union, and this union is a union of intervals, and this is belong to tau, so that this set is an open set. Open set, okay? And we have this definition. Let X and tau be a topological space, and X is a member of X. A set N or a subset of X is a neighborhood of X if there exists some element of topology with this property. This is important. X belongs to a member of topology, and this member is a subset of N. Then this N is called a neighborhood of X, neighborhood, okay? In other words, N is a set that contains an open set, because U is an open set. Any element of topology is open, okay? In other words, N is a set that contains an open set containing X. Containing X. The set of all neighborhoods of an element X will be denoted by N of X. N of X. Okay? Neighborhood. So that, for example, you can write one three is a neighborhood of, for example, 2. So please note that in neighborhood is a set of X that there exists an element of tau such as U with this property. This open set must be within X and N. Okay? Okay? Of 2, for example. Of 2. Because 2 belong to 1, 3, and this is a subset of 1, 3, that one is closed. This is your U, for example, okay? U belong to our topology, and this is N, that is a neighborhood of 2. Okay, so that you must have a member of topology such that contain this. A member of topology, okay? A member of topology. Or as an another example, this is a neighborhood of of, for example, 3, because 3 belong to, for example, 2 infinity, and this is a subset of 2 infinity, and this is open. This is an open set in Euclidean topology. Okay, and the set of all neighborhoods of an element x will be denoted by n of x. And definition, sorry, okay, definition, let X and tau be a topological space. We say that a subset f of X is closed when its complement is open, or its complement belong to tau. So that we have this is the definition, that A is closed if and only if x minus a is open. Okay, and we know that this meaning that this set belong to 2, so that a is closed if and only if this belong to 2. All of this in a fixed topological space. Okay, in a topological space. For example, in Euclidean topology, Z is closed okay, because because we see that this is open. Okay, since this is an open set in Euclidean topology, so that Z is closed. Or as in another example, minus infinity and 1 is closed because we see that 1 plus infinity is open. Okay, we see that this. Okay, for example, this is in the Euclidean topology, so that this is open set. Okay, since this is open, its complement is closed, but the complement of this set or R minus this set equal to this set. Okay, so that this is closed set. This is a closed set. The complement of this open set is this closed set, and this is a closed set in this topological space. So that you can take many examples of open sets and closed sets. For example, if we consider n equal 2, then any union of these squares are open set. Okay, and also its complement is closed, and also in n equal to 3 and other dimensions. For example, this is closed in Euclidean topology on R2. Okay, because this set is open. And other examples. Okay. Welcome, Mrs. Acid. We see another example in R with the Euclidean topology. The set 0, 1 is closed because its complement equal to this, and all of this is are open. Okay, which is the union of two open intervals, so that this is open and so that its complement or 0, 1 is closed. Example, in X and P of X, if we consider topology whole of P of X or discrete topology, every subset of X is closed. This is the case because for any F, we have X minus F belong to P of X. X minus F belong to topology, so that X minus F is open, so that F is closed. So that in discrete topology, it is important example. In discrete topology, x and 2. Any subset of x is open and any subset of x is closed. This is very important because in this case tau equal to p of x, so that for any subset of x we have a belong to tau, so that a is open. Okay, a is open. And also for any subset of x, its complement is a subset of x, so that its complement belong to p of x, so that its complement is open any element of or topology is open. Okay, so that f is closed. Any subset of x is closed and any subset of x is open in discrete topology. In discrete topology. But if we consider indiscrete topology, if we consider indiscrete topology, only open sets are empty set and whole of x, because tau equal to this, and only closed set are these two sets. Okay, empty set and x are only open set and closed set, because if f is closed in indiscrete topology, its complement must be belong to tau, but tau equal to empty set or x, so that this f must be empty set or x. Okay, okay, we can continue in the next session because many students are absent in this session. Let me write Okay. Many students have problem by this time, so that okay. نوافق على تغيير الوقت في واتساب. Okay. Do you know? Do you know? Are you agree with this, dear students? Are you agree? هل أنت موافق؟ Okay. 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 We continue in the next session because many students are absent in this session. Thank you very much for your attention and goodbye for now. Goodbye. Thank you. Goodbye.